Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineers and Computer Science. In this lecturette, I'm going to introduce you to regression analysis, which is a very popular technique that is used in various disciplines to develop some sort of a formula that can explain the underlying phenomenon. Specifically, this is how a regression analysis is defined. It's a statistical tool that is used to evaluate relationship between a dependent variable, let's call it y, with a set of independent variables such as x1, x2, x3, and so on until x of k. I have performed regression analysis extensively during my graduate studies, specifically for my PhD dissertation, where I was interested in devising regression models for predicting the application's runtime on supercomputing clusters, where applications runtime may depend on certain performance parameters for an application, like how many floating point operations they are performing, how many bytes they are consuming, and so on and so forth. Regression analysis is quite universal. It can be applied in so many different fields and for so many different reasons. So let me show you, or let me discuss with you, some reasons why a regression analysis can be a useful statistical tool and in different fields. For example, consider application 1. Let's say that you want to characterize the relationship between independent variables and dependent variable. For example, let's say that you are a civil engineer. You may be interested in studying the beam strength, which can be a function of the horizontal stress and the vertical stress on that beam. So you may perform a lot of empirical studies and calculate or quantify the horizontal stresses and the vertical stress and find out what the beam strength is using your own set of experiments, and then you can use that data to fit a relationship between the dependent variable beam strength and the independent variables, the horizontal stress and the vertical stress. Application 2, let's say that you want to determine a quantitative formula that can help you perform some predictions for your underlying experiment. For example, as a computer scientist, I am interested in runtime of applications on supercomputing clusters. And the dependent variable here is essentially the runtime, and the independent variables are flops, which implies how many computations my program is performing, and bytes, which denotes how much data that my program is consuming from the main memory. So I can perform empirical studies and devise a model that can help me predict the runtime with respect to flops and bytes. And regression analysis is going to help me with this task. Application 3 is, let's say that you want to determine which one of the independent variables influences the most the dependent variable, which of these independent variables is going to change the values of the dependent variable the most in a very drastic manner. For example, let's say that I'm interested in studying the weights of several individuals, and there can be several independent variables that affect the weight of an individual. It can be height of that individual, it can be the caloric intake of the individual. Let's say that these are the two independent variables, and I can use regression analysis to find out which one of these two variables, the caloric intake and the height, affect the weight of the individual the most. So, for example, I can conclude using my regression analysis that the weight of a person actually depends on the caloric intake the most. So regression analysis is going to help us perform that. So these are the multiple uses of why you would use regression analysis. And as I mentioned, it's a very, very useful statistical technique. The underlying math behind it is quite simple, in the sense that we are just trying to apply a straight line relationship between the dependent variable and the independent variables. But how that math is performed under the hood is quite complicated in nature, which we leave for it to be performed by our R software or some other statistical software that you may use in your workplace. So this is how regression analysis usually goes. So you will always have a set of independent variables. Let's call them x1, x2, x3. So these are my independent variables, and you will have a dependent variable. Let's say the variable y. And we are wanting to devise some sort of a relationship between y and x1, x2, and x3. Something that can help us predict y in terms of x1, x2, and x3. So first things first, we work with an assumption that y has a straight line relationship with variables x1, x2, and x3. For simplicity, just consider one dependent variable and one independent variable. So our initial assumption will be that y is just a straight line function of x. So y is equal to ax1 plus b, where a is the slope of the relationship and b is the intercept. So that's your simple linear algebra being applied here. So we are going to assume a straight line relationship, and then using empirical data, using different values of x1 and the observed values of y, we are going to identify what are the best constants a and b that can appropriately help us explain y in terms of x1. So that is called as fitting the model. So we are trying to find the best estimates for these regression coefficients a and b. After finding these regression coefficients, we'll actually check whether these regression coefficients help us satisfactorily model this random variable y or this dependent variable y. If it does, then we are done. If the model is appropriate, then we are done. If the model is not appropriate, what we are going to do is we are going to assume a new model. Perhaps we are going to have some tweaks to this model. For example, I can introduce a squared term, for instance. So my new model will be a1x plus b1x squared plus c. Then I'm going to test if this model helps me explain this independent variable y. If it does, then I'm going to stop. If not, then I'm going to go back. Usually what scientists do is they may try to make these models more and more complicated, which I do not recommend. Complicated models are not the best all the time because complicated models often lead to overfitting of the data. Instead, what I recommend scientists and engineers to do is look for some other variables that can possibly help this random variable x1 to better explain the dependent variable y. So take a look into your experiment, identify some more set of variables that can help you explain y properly, or that can help you devise a model to predict y properly. So that's the general workflow as to how regression analysis is performed. Before we proceed any further, let's review the statistical properties of a straight line, because the goal of linear regression is to fit a linear line. The goal is to fit a straight line. So we will be devising a model which is going to help us predict y, and the regression coefficients are, in terms of mathematics, beta naught and beta 1, where beta naught is the intercept and beta 1 is the slope. So that's simple. That's the simple straight line and its properties. Beta naught is the intercept and beta 1 is the slope, which we would try to identify in order to create a model that explains or that helps us predict y in terms of random variable x. When we perform linear regression, there are a set of important assumptions that we usually make so that it helps us perform some advanced analysis on our models, for example, residual testing, to perform some other hypothesis testing with our model. So regression analysis takes these following 5 assumptions. The dependent variable y is definitely going to have a probability distribution. So y is going to have a set distribution. That's quite simple assumption. Well, most of the things do have some distribution. They are not constants. So y doesn't have to be a constant. It has to be a variable. It has to be a random variable. Specifically, it needs to have a proper distribution. The y values are statistically independent of another, so that's another important assumption. This assumption may not hold true all the time. For example, if I were to measure my weight today, my weight today may be completely different from what my weight is going to be, let's say after 5 days if I'm on some sort of a diet. So my y values are not statistically independent of one another, or my weight is not statistically independent of one another. So carefully analyze your situation and make this reasonable assumption that the y values are statistically independent of one another. For example, when I try to predict the runtime of an application, if I were to run an application today, the application that I run sometime down the line on the same machine is going to be somewhat similar if the application has not changed and the underlying hardware has not changed drastically. So for me, such assumptions, why the runtime is going to be statistically independent of one another. So carefully analyze for your field whether or not this assumption is valid or not. If this assumption is extremely not valid, then you may want to resort to some other statistical techniques. If it is reasonable assumption, if you have a gut feeling that it's okay to assume that y values are statistically independent of the other, then by all means go ahead and perform regression analysis. It's a very robust method. The mean of y is a straight line function of x. So you have x on the x-axis and you have y. So y is going to have certain distribution following assumption number 1 for different values of x. It's going to have certain distribution. What point number 3 is telling you here is that the mean of y is going to be lying on a straight line for different values of x. So mean of y is a straight line function of x. Assumption number 4 is that for different values of x, the variance in y is going to be the same. So all of these are going to be same distributions and they are going to have the same variance. That's another assumption in regression analysis. That assumption is made to perform some advanced statistical hypothesis testing. And then the final assumption is for any given x, y is normally distributed. It's going to have a bell-shaped curve. So for example, if I were to perform my runtime analysis for a given problem size, I'm going to generate different values of y. Y is going to be random. Specifically, it's going to have a Gaussian bell-shaped curve. Now, this is one of the reasons why oftentimes you're asked in science and engineering to perform repeated experiments and take the average, because by the central limit theorem, when you perform repeated experiments and take the average is going to be normally distributed. Because when you perform the same set of repeated experiments the other time, you may get different averages. But those different averages are still going to follow a bell-shaped curve based on the central limit theorem. In fact, I had given you a task, if you recall, early in the semester, where I asked you to perform an experiment that is akin to rolling a die a certain number of times. I asked you to roll a die 6 number of times and take the average. Each one of you actually gave me a different average. And in fact, when I plotted those averages, when I constructed a histogram of those averages, I got a normal distribution. So that's assumption number 5, that for a given x, y is normally distributed. Now let's see how regression is actually applied in science and engineering. We are scientists and engineers and we would like to perform our actual experiments. So let's see how the regression is applied. The ultimate goal for regression analysis is to identify the values of beta naught and beta 1. So let's say that you are a civil engineer who has performed some analysis on a beam, right? So pardon my civil engineering understanding here. Let's say that this is your beam here and you would like to study how the stress changes on this beam, or how the strain, or let's say we want to quantify the strength of this beam based on the vertical stresses and the horizontal stresses on this beam. So you may perform some controlled experiments where you can quantify both the horizontal stress and the vertical stress, and you get different values, let's say x1, x2, x3, x4. Let me not call x1, x2, let me call it something else. This is variable x1, capital X1, this is variable capital X2, and the values here are x1a, x2, x1b, x1c, x1d, and here I have values x2a, x2b, x2c, and x2d, and corresponding to the horizontal stress x1a and vertical stress x2a, let's say that I can quantify the strength of the beam. Let me call it the variable y as y1a. That's the observed value. For this one, x1b and x2b, the value is y1b, y1c, and y1d. 250. Now, using this data that you constructed by performing experimental studies on this beam, I would like to identify the values of beta naught and beta 1. And this is how I can do that. Let's say that I hypothesize a model with coefficients beta naught and beta 1. So the Y prediction based on this model will be beta naught plus beta 1 XA plus beta 2 X2A for X1 and XA, X1A and X2A as my horizontal and vertical stresses. It's going to be beta naught plus beta 1 X1B plus beta 2 X2B and so on and so forth. Now the goal is this prediction to be as close as my observed values. And in order to quantify how well are these predictions close to the observed values, a simple method is to just subtract the predicted value from the observed value or vice versa and find out and perform some sort of an analysis there to minimize that error as much as possible. So essentially this is what I'm trying to do. I'm going to do something like this. I'm going to determine a statistical parameter called sum of squared errors, which is summation the observed values minus the predicted values, which are beta naught plus beta 1 of let me call it x1 of I plus beta 2 x2 of I squared. So this is sum of squared errors, and this sum of squared errors should be minimized for a specific value of beta naught and beta 1. If I were to consider just one single dependent variable and just one single independent variable, let's say y and x1, my sum of squared error is going to take this form, where y of I is my observed value from my scientific experiments, and beta naught plus beta 1 I of x of I is my predicted value. So the error is y of I, which is the observed value minus the predicted value. It's often useful to square it so that I am able to account for both the positive and negative errors. So I square it, and when I sum them all together, I get sum of squared errors. For a very good prediction, the sum of squared errors should be minimized. And I need to find the values of beta naught and beta 1 that minimize the sum of squared error. So the technique is to differentiate the sum of squared error with respect to beta naught, with respect to beta 1, set these individual terms to 0, and then you can identify the values of beta naught and beta 1. So I'm going to differentiate this with respect to beta naught and set it to 0. I'm also going to differentiate SSE with respect to beta 1 and set it to 0. Using these two equations, I'm going to identify the values of beta naught and beta 1. That's how you perform regression analysis mathematically. Just imagine what is going to happen if you were to perform this vast experiment consisting of 1,000 points. Will you be able to do it on a pencil and paper? The answer is no. But instead, we need to rely on a statistical software that can help us perform this kind of mathematics under the hood. We are engineers. We apply mathematics for meaningful results. So we are going to have R perform this sum of squared error minimization and devise linear regression models for us. This technique is called as the least square error method, or LSE method, of identifying the regression coefficients beta naught and beta 1. So the whole goal of regression analysis is to identify these regression coefficients that help us determine the dependent variable in terms of independent variables. In R, we perform these following steps to perform the regression analysis. Step 1 is to read in the data and read in the variables. This step is quite simple. You will be using functions like read.csv to perform this task. The next step is to get the feel of the data by plotting the dependent variable with the independent variables individually. So that gives you some insight into what kind of model you need to apply. For example, if y is related to x, something like this, then I know that a linear relationship will be the best one to be fit. If y and x are related something like this, then I'll say that some sort of an exponential distribution has to be fit. So I need to perform my linear regression accordingly. Using step 2, you can guesstimate what kind of fit you need to perform, and then you fit the model using a function called LM in R. So LM helps you to fit a model between the dependent variable y and independent variables. You'll find your model and identify how good it is. If it is not good enough, then you go back and make tweaks to your model and refit the model. And this is an iterative process which ultimately stops when you can no longer improve your model, or until the point where if you were to perform some additional tweaking, your model may get too complicated unnecessarily. Okay. So let me show you some examples of how to perform this analysis. Let's say that I want to analyze the blood pressure of individuals with respect to their age. So I want to quantify, or I want to devise a linear relationship between my dependent variable, systolic blood pressure, with respect to age. And let's say that this data is present in a CSV file called bp.csv. So I'm going to read the CSV file. This step is very common. You have already seen so far when you are performing hypothesis testing. Next, I'm going to read in the variables into my own user-defined variables so that I do not inadvertently change the data that I just read. I don't want to do that. So I would read these variables into my own variables, and I'll call them SBP and age as well. Step 2 is to get a feel of the data. And to get a feel of the data in R, you just use one function, which is called plot. So if I want to plot age versus systolic blood pressure, where age is on the x-axis and systolic blood pressure is on the y-axis, then I'm going to use the plot in this manner. So this plot is going to give me age versus systolic blood pressure. It's x versus y. So age is going to be my first item. Systolic blood pressure is going to be second. X-lab denotes the label for the x-axis. So when I set X-lab to age of the patient, this guy is going to get the nice label in our age of the patient. And similarly, Y label is systolic blood pressure. If I would like to give a main title to this graph, I can give it in this manner: age versus systolic blood pressure. So it's going to generate a nice, beautiful production level plot that will be having the labels, the axes labeled. It's going to have a nice label to this entire figure, and it is going to plot us the relationship between X and Y, a scatter plot essentially. So that's step number 2, that gives you a feel of the underlying data. Then step 3 is to fit the model using LM function, and this is how I fit the model. LM fit is the variable that is going to fit, that's going to store my underlying model. LM fit is equal to, LM is the function, LM is the R function that you use to fit a linear model. The first argument is your dependent variable, which is a function. So tilde sign here denotes a function. So SBP is a function of age. So that fits the model. And if I would like to summarize the model, if I would like to find the properties of the model, I just type summary and pass LMFit as an argument to this function. So it's going to give me a nice summary of my model. Now, how you analyze this summary is the most important task. As I mentioned before repeatedly, when you perform statistical analysis using R, the usage of functions is not a big deal, but the analysis is what is the most important item. So when I print the summary of this model, there are going to be some important things that you should be looking into. After all, you're trying to fit a model which is SBP is equal to beta naught plus beta 1 of age. So when you look into this model summary, you'll see these terms, intercept and the variables like that. The estimates column give you the beta naught and beta 1 values respectively. So 98.71 is the intercept and 0.97 is the slope. So my model essentially is 98.71 plus 0.97 times age. So these are the estimates of my regression coefficients beta naught and beta 1. Next important item that you'll be looking into is the probability values for these coefficients to be 0. These are the probability values that my regression coefficients beta naught and beta 1 are equal to 0. So if I were to ask, hey, what's the probability that beta naught is equal to 0? That probability is actually this very small value, 1.28 times e to the negative 10. Similarly, if I were to ask you, hey, what's the probability that beta 1 is actually 0, which essentially tells you that age does not help you predict the systolic blood pressure, well, that probability in this case is 7.87. So these probability values right here, they help you determine how important these regression coefficients are. If these probability values are higher than 0.05, or if they are higher values like 0.3 or 0.4, then that means that these regression coefficients, beta naught and beta 1, are not useful to help you predict the dependent variable. R also gives you the significant codes. So when you see a 3-star, then that means it's all great. That's wonderful. Beta naught and beta 1 can be used to explain the dependent variable, systolic blood pressure in this case. If your value is 0.001, it is still good. 0.01 is good. 0.05 is where things go a little bit in a gray area. You may either accept your model or you may not want to accept your model. And other significant codes like 0.1 and 1 should be avoided altogether. So for example, if I were to get probability value for beta 1 being equal to 0 as 0.08, I personally as a statistician would avoid that model and find some other model to fit. So that's the second item that you should be interested in after identifying what are the coefficient values for your linear model. Find out whether these coefficients are significant or not. So these probability values tell you whether coefficients are significant or not. Then finally, the last item that you would like to check for sure is the multiple R squared and the adjusted R squared value. The multiple R squared and the adjusted R squared value usually are quite close to each other. I would not go deep into the statistics as to why it is called as an adjusted R squared, but we mostly rely on the value of multiple R squared. The value of the multiple R squared gives you how much the model is explaining the dependent variable. So in this case, the multiple R squared is 40.4324. So here I can say that this model, which is 98.71 plus 0.97 systolic blood pressure, explains, not systolic blood pressure, sorry, age explains systolic blood pressure's 43% variation. For practical purposes, it is very small. So this model is explaining the variations in the systolic blood pressure only 43%, which is actually a small fraction. So you would want to have a model that has higher multiple R squared value, more close to 1. Exactly equal to 1 is usually practically not feasible. You may get R squared value that are equal to 1, but practically speaking, you may be looking at R squared values like 8.83 or 0.74 or 0.65. These values are good as long as they are above 50%. So statistics really helps you to make decisions. And when we work with uncertainty, it's up to us to determine when to draw a threshold line. For example, I, as a statistician, I usually draw my line at 75%. If a model can explain 75% variation in my dependent variable, I'm actually happy with that model because I just need to perform some predictions and make a judgment as to what I should perform next. So these are the 3 items that you should look into to perform model selection. You look into the individual regression coefficients, you find out how significant these regression coefficients are, and then you finally find out how this entire model is significant itself. So these are the 3 steps that you should be looking into when you look into the summary of the model that you have fit. You can perform prediction using this model in many different ways. A straightforward method is to directly use whatever formula that you have identified and just plug and chug the values. In R, there's more sophisticated method. For example, there's a function called predict, which helps you predict the dependent variable given the independent variable. So I can create a new data frame where I would like to predict the systolic blood pressure for age equal to 40. And then I can use this function called predict. I supply the linear model that I fit, the new data frame comprising age is equal to 40, and I would like to perform a prediction. So this prediction is going to give me a nice confidence interval. So this is my 95% confidence interval. So this interval has 95% chance to contain the true prediction for the systolic blood pressure. By actual plugging and chugging, this is the systolic blood pressure that I found for age equal to 40. So this is an introduction to R. So this lecturette tells you why, or rather this lecturette tells you or gives you an introduction to regression analysis and how regression analysis is performed in R. In my next lecturette, I'm going to show you the step-by-step procedure as to how to perform these individual steps 1, 2, and 3, and 4 to perform predictions. And we are going to look into problem number 14.1, and I'm going to post these CSV files on Canvas so that you can work along. I think it's a good time to stop this lecturette video right here.